Lublinerman, and I joined the WIT team 6 months ago, and that was my first contact with WIT as well. So, and I mainly work on compiler and compiler stuff. So now I want to try to give an overview on how the compiler works internally. So you can stop me at any time. I have more. There are parts that I know better than others, so correct me if I make a mistake. And here we go. Here we. So basically, there are these 3 components. One is the compiler, takes the Java code and outputs the JavaScript code. There are some libraries. Some libraries are unnecessary for the compiler. They help the compiler. Some are like the emulation libraries from the Java. Some are other user libraries. And there's the runtime, which uses small pieces of code that help the application get started. So the compiler has 3 very distinct phases. The first one, the precompile, is the phase that tries basically to get all your Java sources, run your generators, parse them, and build an initial AST. The second part, the compile permutation, starts from the AST and runs all the optimizations, turns this Java AST into a JavaScript AST, makes some more optimizations, and then produces the JavaScript code. And the linker gathers all the information from all the permutations and bundles it up so that you can run your application. So let's dive into the compiler. So the first stage, the precompile, as you can see, it's pretty complicated. So you start, well, you just determine what are your options. That's the hard handler's part. Then the compiler goes and tries to load the module definition files to see whatever needs to be compiled and compute the resource oracles. You build
what a resource oracle is. It's basically kind of like a virtual file system. It's basically an abstraction for knowing like what is essentially the inputs to the compiler, and you can check when things have been updated and whether or not what their last timestamps are.
Yeah, and so you, then you start initialize the completion state builder unit cache. So we cache lots of this stuff. So maybe you also have more to say about the cache.
Well, the unit cache in particular is used to speed up like dev mode. There's one called persistent unit cache. So like so after dev mode has recompiled some of the classes to bytecode, and the next time you launch dev mode, you can basically read those off the disk, so the startup time is faster. But essentially, the compilation state builder is a wrapper around the GWT compiler. And if you don't know what the GWT compiler is, it's essentially the Java C implementation that sits inside of Eclipse that recompiles classes on the fly. We use the same thing that Eclipse does, compile Java, to actually get at the partial representation of Java.
Yeah, there are some subtle interactions. So we call the GWT compiler to compile, and it calls us back to get more stuff, and that goes back and forth. And then the actual precompile phase begins. We load the serialized guitar, which are so these are modules that were precompiled before, and their AST was already built. And we also, when we build the AST, when we compile things with the JDT, we store the AST and the class file that is generated by the JDT. Then we start from get combination state. So this is basically saying compile this module, get the results of compiling this module and these triggers, starting the JDT to compile. Then we need to compute the permutations and run the generators. When these generators are run, they produce more files that we need to look at. And each time these files are added to to the set of things that need to be compiled, they will be compiled and the cycle continues there. Some permutations I know nothing about, so maybe you can say something about that.
It's probably not important.
Not important
right now.
Okay. At this point, you have a lot of AST for each of the classes that you compile. You may even have duplicated parts of it. You may have compiled things for the server. You may have many things. And the Unify AST will traverse from entry point and try and resolve, bind these different AST together. So if you compile an AST and it doesn't really point to the other, you compile one class and the class refers to another class, but this reference is not a pointer at that point yet.
So it's a reference by string. So this was added. This was added. This step, this Unify ST step, when we were going to start doing incremental compilation with GWT files. So GWT files basically are the compile module phase. So you take a module, you compile it, and you don't do optimizations. You immediately just write out the GWT file. But then later on, when you have another module that uses those GWT files, they no longer have hard internal like Java references to the other parts of the AST. They have strings, like class foo that uses called the method on bar will literally have a reference in the AST that I'm calling quote bar method baz on it. And so the Unify AST basically traverses the entire tree from the entry point, and when it finds one of these unresolved reference by string nodes, it basically goes and looks up the real one that's been deserialized from the GWT and starts to pointer to that one. And so that's basically the purpose of that. And then so after Unify AST has been executed, you now have a whole program view of the entire application, and that's when you can really start to do stuff.
Yeah. So then you compute the J-type oracle, which is not the same as the type oracle seen by the generators. This type oracle, J-type oracle, has some sort of summary information about the whole AST. For example, it knows what classes are, what are the superclasses, what are the subclasses. So it keeps track of the static initializer. So it has a lot of different things that it keeps tracks on that it's needed for the optimizations later on.
Simple example would be like asking whether one class is a subtype of another, or which interfaces or superclasses a given type has.
Yeah, and some of this information may get invalidated by the compiler, by the optimizer, and needs to be recomputed. And some it's not. Current passes do not invalidate it, so it's not recomputed. But if you modify the passes, you need to look at the type oracle to see if you need to do something. Then we perform a few passes on this unified AST to make it more to remove stuff or change things. So we do some unboxing on some of the. So here, for example, if you do a ++ on a box integer, so here is the place where we unwrap that and unbox it. Most of the unboxing is actually done in the Java, at the phase where we generate the JavaScript AST. But there are two, which is this. I think it's the ++ and the plus equals and minus equals that we treat in that one there. Then the next one is either remove all the assertions or implement them as. I think we'll replace by a function call, I would suspect.
To the exceptions.java intrinsic class. Okay. All the assert foo methods are in there.
Hey, Robert?
Yeah.
I think you can talk from there, should be closer to the pickup. So I don't know how.
Oh, sorry.
The
so
recording
yes,
is coming.
because I wanted to.
Oh.
I prefer looking at there. Then we run the optimization loop once. There's no real reason why we do. I've been running experiments, and if you take it out, don't take it out, it doesn't make much of a difference.
I think the original theory was that when we're starting out the compiles within Google to like many to many machines, if we run one small optimization loop before we hand off the AST to like n different machines, they each will have like a smaller chunk to deal with. Because remember, you start out with this big blob of classes, which are all the permutations together. Like all of the dominants are in there, all four of them, right? But then on a per permutation basis, each of them might not, only really need to look at a subset of those. So the idea was like to pre-prune some of them, so the individual permutations will run faster. But it turns out that actually doesn't really.
It doesn't really matter, and actually it makes your serialize. So if you do like, for example, serialize, so you could run this precompile and compile in separate phases, in separate processes for serializing and deserializing, and this AST after this first loop is actually bigger than the one before doing the optimization, because the first pass does creates all the statics and all that, and then we record all the rewinds, so we record all the places where there are we create that these need to be replaced on a per permutation basis, so they cannot be done at the precompile, because here we do things that it's permutation agnostic, it's valid for all permutations. So this part is very kind of complex and intricate to modify. So here's where we need to touch for the incremental compile to become a reality. So next part is to compile a permutation. So you start from this huge AST that has all the permutations. So the first thing you replace the revive, so you make that permutation real at that point. So now you have an AST for a permutation, and then you start the process of optimizing this AST. And there are two distinct parts. One is done in the Java AST land, and the other is done after we go to JavaScript. And they're mostly, for most things, they're completely independent except for the code splitting. So once you have the AST for a permutation, we run the optimized loop, and this we run until no further optimization opportunities are found. After the code is optimized, we run some normalizations, and I'm going to go in detail. So this will make the AST simpler for the translation to JavaScript. For example, one thing that we do there is if you have catch blocks, we transform if you have several catch blocks for a try, we transform it into just a single one to mimic what you have in JavaScript, to make it just the code for the translation it becomes simpler. And then we transform the Java AST into a JavaScript AST. So one thing to note is whenever we're doing stuff with the Java AST, we, for most part, ignore all GSNI code, except just taking into account that you have references there to compute liveness and all that stuff. But basically, we don't touch GSNI code in the Java AST. So, for example, if we do inlining, and you have a piece of GSNI code that it's just a getter, that won't get inlined. At that point, it will get inlined.
Give me the function that has
native JavaScript.
the method that has
the method that is Java. That method is not inlined, and if it calls a Java method, that method is also not inlined. So it breaks like the inlining barrier in that sense. Then we translate the Java to JavaScript. And we run a bunch of passes of there. Normalize. I forgot what the normalize. What does the normalize do?
So the JS normalization pass is basically.
Oh, those are the normalization passes.
Yes, and they fix something. So when we translate from Java to JavaScript, some of the structures that come out of there can be incorrect for JavaScript. For example, the L values. There can be things on the left-hand side that basically don't work. For example, like you'll have a CL in it on the left-hand side, like a common expression, and the assignment won't work in JavaScript. And so, like this breaks up the L values on the left-hand side and things like that.
So, yeah. Okay.
Basically, the AST that comes out of the generate JavaScript AST pass actually is not legal JavaScript. What JS normalizer does is it fixes it.
Then we run the symbol resolver that resolves references. So one big difference between Java and JavaScript is in Java basically there are very few scopes. So you have the method scope, and that's probably where you look everything up mostly. And in JavaScript, you have a hierarchy of scopes, so you may have nested function literals, and these define different scopes. So the symbol resolver basically tries to fit each of these references into the appropriate scope, so that later, when we do the renaming, you can make clashes for things that are not accessible through the same scopes, and that you reduce the size of your symbol names. Very important, it seems. Then we run the JavaScript optimizations. In this case, it's just 3. One is basically does the dead code elimination and constant following. We run the inliner, JavaScript inliner there, and we remove unused functions. And then we run the code splitter. The code splitter, we use information that was from the Java AST, the liveness information. Our control flow analyzer works on the Java AST land. So we use information from the control flow analysis on the Java AST to know what parts of the JavaScript program go into each fragment. And we'll go into detail. Then we run a few passes of browser fix-ups, which I want to take them out of the global equation and put them in make them like user passes. Because some fix things that are later, so fix things for a specific browser, specific version that probably...
A specific nightly build version of Safari that had a bug in Nitro KIT.
Yeah, another was another version that had a bug on the ++. Yeah. And they were doing a patch for that. So this, I think it's better solved by having a plugin fix-ups, and you can write your own and put it there, and it will be run. And if it's not there, we don't run it, and then we don't have to even maintain it once it's obsolete. And then the namers. So we have different namers. One replaces all things by obfuscated names to try to make the names as short as we can. Or we can get pretty detailed names. So this is the namer does that.
Roberto?
Yeah.
How do you decide which optimizations to run for Java and which optimizations to run in JavaScript?
Oh, so, this was decided on the design of the compiler. So these are fixed.
Right, but what's what's the reason for some of them being in the JavaScript?
Okay, so the reason is the GSD code. So we write this Java that's annotated with JavaScript. And our Java optimizations they don't know the JavaScript model, so they don't optimize those parts. And
also, a lot of the optimizations on the Java side are type specific, actually. If you didn't have the types, basically, you wouldn't get as much of a gain. It's kind of different than the closure, where the types are more for validation and not as much for optimization.
Yeah, and the JavaScript optimizations tend to be more limited scope of more people type optimization.
yeah, and more expensive because the AST is more bigger.
Well, I mean, some of them you can't necessarily do in Java, but also you wouldn't be optimizing any business code.
Well, in any case, we would prefer to do so with in the richer type system with Java, we have more opportunities to optimize to prune code out.
Well, I mean, some of them you couldn't do in Java AST because it wouldn't be legal. For example, variable like register allocation, like closure, like reuses local variables in scope because they have types. So, for example, if you have int x. And then later on in the method, you have string y equals something. The closure compiler will get rid of the declaration of the var y if it's no longer, if the x is already dead at that point. In the method, it will only just have one var because it can reuse x for 2 different types. Because JavaScript supports union types, whereas Qt doesn't support that. But the real answer, just quickly, is the fact that I think the JS AST was a later addition to the Qt compiler. And so really, if Qt team had collaborated much earlier with the closure team, probably the better thing to do would have been to actually have closure as the back end optimizers instead of duplicating them. I think that's like a goal for the future, is to try to merge closure as a back end.
And we don't do many optimizations. We don't do much on the JavaScript code either.
Our JavaScript test is suck, basically.
Is it possible to take Clojure and run it on the JavaScript?
Yeah, so we have an experimental option to run Clojure. You lose in the implementation that we have. We haven't fixed up the source maps and the sorry that gets screwed. But,
it gives you like a minimum at least 5% size.
Now, the problem
Normally that's much
at least
larger.
Last time I looked at it, adding a closure pass was really, really slow.
Well, that's because we have all optimizations turned on. If we did Clojure the right way, we would not enable Clojure optimizations that are redundant to what's already been done in the Java ASD. We'd only turn on the ones that actually we're not doing. That makes sense.
and actually,
Then you don't get any optimization.
but the other thing is that
For what?
Because we obviously can't do any optimization on Disney in the Java pass.
Yeah, but Clojure has a lot of passes that we can selectively enable that actually would do a good job on the output. And the Clojure run like Wood actually has like a lot of flags that you can flip on and off, like dozens. It's very fine grained, so you can just turn on one or two passes that you want.
And also, we would want to skip the type inference, which also takes a lot of time in Clojure. You already have all the types almost
So
everywhere
you probably want to look up the type information from the Java ASD.
from the Java SD and annotate it for Clojure.
So what's actually missing on tracking the optimizations to compile report would be working?
I think we should do this after because this is a long presentation. It's like 40 slides, and each slide takes a long time. So like we won't have we're running out of time. Like
No, okay. So
yeah, you should go forward.
so this is a picture of the Java. Well, it's a little bit small there, but that's basically the Java big picture of the Java ASD. So you have the types, the variables, and the statements and expressions. So these three and the last one here are like the basic construction in this ASD. So the only thing to know, well, so that I don't know if I want to go in detail.
I think it might be better just to actually show the examples. That's much clearer.
Yeah. Okay. So here's how a small class would look like in the ASD. So the class construct would be J class type, which is one of the subclasses of J type. So this one has one method and one field. The method has a method body. So then you have an option. If it was a native method, you would have a GSD method body, and that would be a JavaScript ASD. So this is a Java ASD. Basically, it has one expression. It has one statement, which is an expression statement that turns an expression. So the equal is an expression, and so the expression statement turns the expression into a statement. The expression is an assignment, which was as a left-hand side of x, which is a reference, and right-hand side is the operation. So the important thing here is that the visitor. So whenever you refer to other kind of important thing in the ASD, like fields or methods or classes, you will have this either a field reference if it's a field, a type reference if it's a class, or you have a method call if it's a method. And the visitors, they would stop at that frontier. So if you run a visitor, the visitor will visit all the solid arrows, but not go through the dashed arrows. So this is important because this is actually a graph that has cycles otherwise. So we visit the tree, not the full graph in the visitors. Okay. I don't know anything else from here. So now we're gonna go. How do you write an optimization, and how do you transform the AST? Basically, we do all our work through visitors. There are two types of visitors. The J visitor is just a visitor that doesn't mutate the tree. Normally, a pass will consist of some visitors that collect information about the tree, and then maybe one or two visitors that really mutate the tree. Normally, we have one that does the optimization, and then probably, in some cases, one later on to fix up some things that the optimization couldn't do at that time. In this case, we're writing a very simple constant folding. So this we just need one visitor. So we extend the mod visitor. We say just in the visit of the binary operation is where we want to be. And the way to mutate this, for most things, the way to mutate this AST is to replace the node you're at. So here you say, well, okay, so I'm at the binary operation node, and this is the right one I want to change. So I want to replace it by something else.
In general, most of the optimizations are a pattern match. You can kind of think of this almost as like a regular expression, just like not very close. But basically, it's like first I want to match any, scan the whole tree and match everything that's a binary operation, plus, equals, or whatever. Then next, if the left-hand side of the operation is a literal and the right-hand side is also a literal, then replace the binary operation node with looking up both literals, get their numeric values, which in this case is 2 and 5, add them together and replace it with 7, basically.
Yeah.
And that's really all of the optimizations work mostly like this at this level. It's complicated pattern matching.
Yeah.
There's the more complex ones have to deal with global information, but a lot of the local ones are very simple like this.
Yeah.
For this, constant folding, do you go to a fixed point or do you do one pass?
We fixed point.
Well, we normally do a sequence of optimizations. We don't fix point each one.
Okay.
Normally, I think this one is the constant folder is inside the dead code elimination, so maybe that one we do fixed point there. But normally we do one pass, and we do all the optimizations and then loop over until a fixed point. We have a patch.
What do you mean by fixed point?
Fixed point means
Keep doing work until
there's no more work. Yeah, until there's no more work.
Until you reach a steady state, basically.
Yeah. So we have a patch in the queue that just stops. So you can tell the compiler to stop when there are very few opportunities. So if you did like you have 100,000 node AST and you did just like 100 mutations in last pass, you may want to stop, and you would get back like a 30% of the compilation time, and you would lose maybe 1% of code size. So that's a trade-off that people may want to decide if they want to take.
Because some optimizations won't be detected by the pattern matching. So, like, they'll be detected as a result of the changes that the last pass made. We'll then make another optimization possible.
So there's an example of that where you show all the optimizations together later.
Yeah. So just this is the cautionary things if you want to write optimizations. So you have the J-type oracle that stores pre-computed information that may need to be recomputed. So it has the information about types, supertypes, interfaces, super interfaces. It knows about the static initializer, so it keeps track of which runs are need to be called in which case, so that you don't generate code for things that are empty. Because the thing is that whenever you inline something in a class, you may need to put there the class initializer. So you don't want to do that if it's not really necessary. Purely local optimizations like the one I showed, probably very safe to do, easy to do. You probably don't need to care about anything else. There are other like little things in the compiler. So we have two representations for types. Basically, once we know that a variable, a typeable thing can never be null, then we replace it by a J non-null type of the type class. So if you have to be careful if you want to compare types.
It's not quite the same as Java nullability analysis. We either prove that something is always null or something can never be null. But we don't represent, otherwise it's nullable, I guess, right? It could be null. And then there are things that basically drop out in the optimizations early if you know those things, like we try to do an instance of operational and a null. Well, of course it's always going to fail and things like that.
Yeah, so what else? So I can speak. So then there is this null fill and null method. Sometimes the replace operation inserts, because you remember you're replacing this leaf node somewhere. Sometimes you need to rewrite. So if you want to get rid of something there, you may need to rewrite a big chunk. and that's like more complex. So basically, the optimization decides that okay, so that reference is going to fail if it's executed. So it replaces by a null field or null method, and if the code gets there,
Like an example would be is if the optimization wants to delete something and it's like an inside of an expression like a plus b, a plus a method called a foo, and then at a certain point foo is determined to basically be empty, and so it might want to just remove the method call, but you just can't have a plus nothing. So that's with something there. So it will put a reference to if it proved that like foo is an empty method or a field is nullable, they'll replace it with a reference to a null method or null field. Then later on, in another patch of the AST, some of those will be stripped out. It's just like to preserve the structure, basically.
Some will percolate UVM, right?
Yeah.
And one example is if you ever see in your running JavaScript that it tried to call a null method, that was because typically you get something in Disney passing a null value where it was sure that it couldn't be null.
Yeah. Okay.
And then, well, the special method to clean it is class initializer, and init is instance initializer. So those have to be thread with care, both. Okay, so type oracle and JType oracle, different things. One used for generators, the other used during compilation. What are the optimizations that we do? So the pruner basically runs control for analysis, decides what's reachable, what's not reachable from the entry points, and prunes the things that are not reachable. Finalizer, if you have a class and it doesn't get extended, then we annotate it with final. Some other path will do something with that annotation. If you have a method and it's not overridden, we annotate that with final as well. If you have a field and it's only initialized, then we annotate that with final. Some other paths will do something about it. Make call static. So this basically, okay. So make call static. So if you have a method, polymorphic method, but there is if you have a call that is determined to be static, then that method would have a static version, and that will be called in that place.
If you have a method that is never overridden, which is basically the case for most methods, then they basically get rewritten so that this parameter becomes the first parameter and it's turned into a top-level function. They're basically taken off the prototype.
So this is going to happen a lot for getters and setters, isn't it?
It happens pretty much for every getter and setter. It's very rare people override those. In fact, I would say the vast majority of the methods actually turn into static methods.
And so probably we could share. It's sharing all setters then on a Pojo then.
There is a later optimization called JS duplicate function remover that basically can, rewrite 1,000 setters into one function call because they're all the same. They're all like
same structure.
Yes.
So do you think that because the line to that?
Yes.
Yes, that's where the inliner. So I have an example. So I'm gonna go.
Maybe we should just go to the diagram.
Okay, I'll go to the
All
example.
right, no, keep going. That's
Okay, so type tightener basically, as it says, if you have declared a type for a variable, but you know that it's a type down in the hierarchy, actually what gets assigned always, then you can replace it. Example here, you do object O equal new foo, then type tightener would say, okay, so O is actually a foo. It's always, and that will be used later to devirtualize.
It's a kind of type inferencing, but it's global in nature, not local. So it basically applies across the whole program.
The method call tightener. So you have so independent of what's the instance of a call. So when you wrote the program, we determine what was the target of the call. Let's say you may have. So in this case, you may do a get class, right? Object get class or get class, and we will record that you will call all object get class on O, but on Java object. And then when method call tightener comes down, say it says, oh, so this is a foo reference, so we call foo get class. If it is overridden, we call foo get class, for example. And well, its example is down there, so it's easy. So well, that code elimination does constant folding and removes bunches of statements that are not reachable. This is a very local optimization, very easy to understand. If you want to look at one to understand, that's the one you have to look at.
So with some of these things like the type tightener, if I'm declaring something as object but it's always foo, then, that might be, is there any way to get information out to like tell the developer like, hey, why are you doing it this way? It seems more efficient.
Well, the thing is that it's a common practice in Java to, for example, use the interface type when you declare the variables. And you normally, for lists, you always declare a list of something and then you assign it as some specific list. And that's a common practice. I don't know if you want to make people change that.
And also this changes based on the class hierarchy, right? So you could import another module.
Oh, yeah.
And basically, like for example, let's say you assign you have a method that takes a list, right? And you're importing one module where only an array list is instantiated. Well, a type tightener basically is going to look at that and maybe say that I'm going to change list to be array list. But then you import somebody else's module into your project and they instantiate a mutable list or linked list.
Yeah, absolutely.
Now all of a sudden, so you don't want to get warned by that because if
You
you
get too many.
complaining about that, you're going to get like
And in
that.
some cases, like, you might write 2 plus 3 because there's some semantic meaning to you as a human, even though it's always fine.
Yeah.
So, but, on the other hand, if I just might want to know.
Yeah.
Well,
I mean,
You get thousands of warnings.
I think you could write a static analysis tool. That would be a good idea for a static analysis tool to help you improve your code. Like in IntelliJ IDEA or other IDEs where they're like, they give you a warning or like this line of code could be written to be more efficient or whatever. But,
Okay, so that makes sense.
And here, so the examples are very local, but actually we know exactly what types are available. So sometimes it's not obvious. So you have, let's say, some class list A declared somewhere, and you don't instantiate it over there. But we know that the only thing that implements list interface that we have that we instantiate is array list. Then that will be tightened to array list because we have the global information on the whole program.
Is there anything where it gets more aggressive and says, like, here you're using array list, here you're using linked list, I'm just going to make it arrays?
No,
No.
it doesn't change it. So
Arrays.
if you have 2 different instances of different things that you want.
yeah, but it can type tighten 2 different methods that both take list parameters to be 2 different specific concrete implementations.
Yes.
So it doesn't globally replace list everywhere with the array list. It's specific based on the type flow through the program.
Yeah. So it will do the local.
I think you
local.
should go to this picture.
I should go to the.
When is this? How much longer time we have?
Well, technically 10-15. So
Oh,
okay.
how many more slides do you have?
I think the picture is.
I'll go with it. I'll go.
After the break,
I'll go-
people don't mind.
I'll
we
go
can
to
go
the
like
pictures.
10.
Okay, let's say you start with this very simple example. One interface, 2 classes that are implemented, 1 method that is overridden in both, and 1 entry point, and 1 thing. Very simple. And this will illustrate what passes do. Finalizer, looking at the whole program, can decide, okay, these 2 classes are final, never extended. These 2 methods are final, never overridden. No field, so that's what the finalizer will do here. Type tightener. So you had an assignment foo equal new bar. The type tightener will look at the body of the method and decide that foo always gets assigned a bar, so it will replace the type of foo by bar. But you see, the call foo.m1 still calls foo.m1, not bar.m1. Because that's the job for the method called tightener. We'll decide that because you have a foo reference, you have a bar reference, then the method call actually is to a bar object. Next thing is make call static. So because the call to M1 is to a final method, then that call is a static call. And because it's static, the compiler will decide, okay, so then that implementation of M1 can be made static, and it will explicitly introduce a new the this parameter, and it will name it this static, and copy the method body and replace the method body in M1. In this case, it was empty, so I don't know if exactly that will happen, but imagine that there was some code there. So some other optimization will decide to get rid of it altogether before that. And then it replaces the call from a foo.m1 to a static m1 on foo. Oh, so it will be a bar.m1 in that case. Then the pruner will come in and decide, okay, so this part of the code is not reachable. So now we have this smaller program. And then, well, the pruning runs in a different, that's what the pruning would do. It probably would run at the beginning. Then, because of a static version of M1 is small, you may, or it's empty in this case, the inliner decides to inline it, so it goes away. And if we run the pruning again, then the M1 will be completely gone. And the beauty of these things that they're very simple is that if you, they collaborate well with each other. Especially the one that I haven't put in here, which is the dead code elimination. After you inline, you may get parts of the code that are no longer reachable. And then the control flow analyzer will see that. And you will have lots of new opportunities for optimization. On the downside, so this way of doing like optimizations by visitor is very nice because it's very clear. On the downside, as the code gets more optimized, the visitors are more ineffective because they will visit the whole tree, they will ask a bunch of questions and not mutate anything, and just maybe mutate one method, and then you have to go all over again. So this is one area which we want to improve.
So all optimizations are running in each loop, like you are not disabling some optimizations.
All optimizations, and these optimizations are all running in each loop. We've done some experiments to take, for example, some that normally don't get much gain after the first loop to get them out, like the enum ordinalizer only will be effective in a loop if you have a deep hierarchy of enums, which normally is not the case. Maybe you have one level or two level. You probably don't have a deep hierarchy in enum classes.
Now, there's some general cases where you could prove that this change can only result in further changes, but not this kind of change.
Exactly. So that's one thing that I've been exploring is so you did this change, and you know what it means for other optimizations. But we don't have, for example, we don't have pre-compute so we don't have an actual utilizable call graph abstraction in the way we're doing that. So sometimes you say, okay, so I changed a method body, so I may need to run inliner on all colors, but then I need to know the colors, and we don't know the colors. To get the colors, I need to run. So it's not designed to be that way. So we're working, improving this version and maybe changing some of these optimizations to be work list based instead of visitor based. But
Roberto, you want me to do this slide?
do I want to do this slide?
No, you want me to do it? I can explain it.
You can explain. Yeah. So.
Yeah, so because I worked on the JSO virtualization system, and so one complicated thing is how overlay types are handled in GWT. And so at one point we added the ability for overlay types to actually implement interfaces. And one of the things that people always ask is like, well, why can only one overlay type implement an interface? So this is a restriction in GWT. If you have an interface, any number of Java types can implement it, but only one JSO can implement the interface. And why is that? Well, because JSOs basically, or overlay types, don't have any runtime type information. They don't know what they are. Essentially, they're a collection of static methods. So just think of them as global top-level methods. So if you have a class, let's say it's called DOM element, and on there there's a method called getAttribute. That's not a prototype method on some emitted class where it's like .prototype.getAttribute because you wrote this GWT method. It's really a top-level function like $getAttribute that takes an element as the first parameter. So the problem is that when the compiler is done, all this optimization, it's going to have things where there's an interface dispatch, like interface.foo. And if there are two different implementations of that, one is a JRE type and one is an overlay type, how does it do a polymorphic dispatch, right? Because that variable underneath of it could be a Java implementation or it could just be an overlay type. Well, the overlay type actually really doesn't have an object backing it that has virtual methods on it. It's just a reference. So what happens is the compiler inserts this trampoline. It basically says, is X an instance of JavaScript object? And if it is, then I'm going to just insert a call to this top-level static function that came from the overlay type, the GWT function that you wrote. Otherwise, I'm just going to do a regular like x.m call. And so that's what JSO devirtualizer does. Catch block normalizer, basically, I think Rodrigo talked about this before, but JavaScript has no notion of typed catch blocks. It's just there's just one catch block for a try, and so inside the catch block, the compiler essentially inserts a giant like if-else cascade. It basically says, well, if E instance of Java exception type 1, then this, else this, else this. So it basically does a switch on the type. Long cast normalizer. Well, there's no longs in JavaScript. So basically, if you have someone doing something like casting from a long to an integer on the left-hand side, this basically goes in and inserts a method call to the long-lived library to basically perform a cast. Long emulation normalizer does that, but for like all of the arithmetic operations. A plus B is like a call essentially to like longlive.add. Cast normalizer. JavaScript has no cast operator, so what this does is essentially for every instance of operator or for every cast operation, it makes a call to this magic intrinsic class in cast.java. It has methods on it like instance of can cast type comma type, and it returns true or false. Array normalizer.
That would be if you said -x class disable class cast.
If you do -x disable cast checking, it disables the insertion of the calls to can cast, but it still keeps the instance of operations. So cast normalizer still runs. Array normalizer. We don't, of course, JavaScript primitive arrays are different than Java arrays because Java arrays have types. So when you construct a Java array, you actually have to put some extra variables on it so that, like, if you do an instance of operation on an array, it basically knows what it is.
I ran up against that recently.
Yeah. And so what the array normalizer does is it inserts things like new array square bracket. It replaces it with method calls to like an arrays class, which is another magic class. You can see the implementation of it, but it's Disney methods. And one of them is init dims, which is init dimensions, and the other one's like init values, where it zeroes out or nulls out the array to adhere to JRE standards. Equality normalizer. Basically, this decides whether or not to replace a Java equals with either double equals or triple equals in JavaScript, based on the types of the two sides. And I don't want to get into when or why you have to use each. You might want to look up the presentation called WAT, W-A-T, about JavaScript. But there's a big table on the GWT site that basically lists all of in a matrix, like the various considerations for when you have to do each. And finally, get class overrides. So initially, the object.getClass method is implemented in GWT as an override. So for every type foo, bar, baz that is in the whole system, it adds a method called getClass that returns the class literal. So class foo would have a method called class getClass return foo.class, right? And what this does is, because that would be bloated to have like 1,000 overrides, it basically replaces the getClass call with basically a field reference to this magic variable field called underbar CLAZZ. And the reason why it's called triple underbar is that there's a bug in the GWT compiler. And if you try to name a field on object.java as CLAZZ or even underscore CLAZZ, it basically breaks. But only if the class is called object. So it's that's the normalization. This happens after optimizations. So I don't know if you want to talk about this, the JSAST.
Well, then we have the JavaScript AST. The only difference that most things in the JavaScript AST are the interesting part are expression and are the function literals. That's where the richness of the AST is. And then you have the scopes, so which is where scopes are maintained to know where things are defined at which scope and to know when it's safe to rename, to make a class or not.
One weird thing is that with respect to scopes, JavaScript has certain constructs that introduce scoping, like functions or catch blocks. We actually introduce synthetic scopes that are relevant for Java, but not necessarily for JavaScript. So, for example, we have class scopes, interface scopes, things like that. And the reason why we do that is because we can know that like two different JavaScript expressions, like this.x, the x could refer to something different. So it disambiguates, basically, it allows two different classes to use the same identifier and be disambiguated.
Yes.
How different is this from the Rhino A?
It's radically different. The random AST is like a DOM-oriented model.
So here is an example that which shows what scopes are created for a simple. So this is the Java program. So you have the scopes that are for each class has a scope and it's linked to a parent. So you have a scope for interfaces with all the interface names are in that scope. You have scope for object, which is only special for I think.
Like all the things that exist on Java okay, at the root of the hierarchy is Java-lang object, but above that actually is the JS object, which is built into the browser. And so fields that are on the JS object itself, like dot call or dot toString or dot prototype or the stuff that's built into the browser, sits on the object scope at the root. That's to make sure that we don't accidentally obfuscate something, name something that's basically in one of these built-in scopes. But also, it exists that if someone refers to them, like if you have a Disney method, like way down here, right, and you basically do, object.toString, it can properly resolve it to the a reference to the JS object toString, for example.
And then the other is the functional scopes, and if you have so the two places where we introduced functional scopes are in method. Each method has a function scope, and each catch has a scope, which is a catch scope. And I suppose I will introduce function scopes for function literals when you use that in Disney.
I don't remember.
Maybe So I haven't looked at that either. So these basically let you ensure that you don't collapse. Sorry.
Yeah, actually,
So
like if you happen to have two classes, right, and let's say the field they have one field on it, right, and both fields could be named A, right, and so if the types are disjoint, right, you could rename both of them to the identifier A, but if the types like shared a common superclass, right, then that symbol is not available, right, for you to rename your field into when you're minifying, because basically it's already consumed by something in a parent scope. And so that's one of the primary things for having this scope structure, is to know what you can you can assign, what symbols are available in the scope.
So we want to go.
Well, one last thing is that the scope hierarchy is also used to resolve symbols that didn't come from Java, right? So if you write a Disney method and you just like say, window.alert foo, right? Or like for example, this X is naked X here.
Yeah.
Right? And so basically, the compiler will traverse these scopes looking for a symbol that's been declared in that scope that's called X.
Yeah.
And eventually, in the vast majority of the cases, this will resolve to something in the global scope, right, like on the top scope. But sometimes there's an intermediate scope that might have one of these symbols declared on it.
Basically, if it's qualified, it goes to class path, I guess, and if it's not qualified, it goes to the functional scope. What else? So this I can skip. So this is how I play it, so this you can talk.
Yeah, and so one question a lot of people probably are curious about is like, when you compile a class to Java, what does it actually look like when it comes out in a JavaScript? And this is an example of what it looks like. So if you had a class called foo, maybe it had two constructors, and what would it look like in the output? Well, this is the minimum, in this case it has two fields and two methods. This is the minimum amount of code that the compiler would admit. So this is one of the reasons why overlay types are beneficial, is because if you have just an empty class that you instantiate, and all you do is instantiate it, you're going to get this in the output. And so the first thing we do is we're going to declare the constructors, right? So the compiler will translate the constructors to JavaScript, and you'll get these two functions, constructor 1 and constructor 2. Then the next thing we do is we need to set up a prototype, basically to hold fields and methods. And so there's this magic class called seedUtil, and it calls a factory method called defineSeed. And one of the things we do at this stage is, every class has been given a type ID, a number, 1, 2, 3, 4, and 5. And so this method this code is emitted, which basically is the type ID of the class, the type ID of the superclass. For example, Java Lang object is 1, I believe. String is 2. There's like the first two. There's 2 of them that get assigned by the number by default. And then castable type map is basically a JSON object, which represents the set of interfaces that this type could be cast into, as well as the immediate superclass. And then finally, the 2 constructors are passed in. And so what does this thing do? This define seed function basically creates an anonymous function, sets its prototype to be the prototype of the supertype ID, assigns the castable type map onto the prototype, and then sets foo constructor and foo constructor 2 to have the same prototype as the factory function.
So instance of would work in JavaScript.
No, instance of would not work because the 2 different constructors would have, I believe, when instance of operator basically does like prototype.constructor to do the comparison. The native JavaScript instance of operator.
I think so, but I think the
Oh, that's
problem
being
Yeah,
I believe the native built-in JavaScript instance of operator does the equivalent of .prototype.constructor and looks for like this string comparison. So WIT cannot rely on function constructors to define the type. The type actually is done by this castable type map and these type IDs. That's how it knows what it is. We could change the encoding, but it would be more bloated. Okay, so then you get the 2. So that seed util.
So what does seed mean? Why use the word seed?
Probably a bad name, but basically it just creates an empty function prototype that's the seed for patching all the other stuff onto it. So anyway, it sets up this underscore value, and then you can immediately just set the fields and methods onto it. Then finally, if the class has a static initializer, there's a CL init method generated. Like so, if you have something like static foo x equals new foo, like a field of one of your classes, there's a CL init that's generated for it. The first line of the code assigns itself, so it's self-modifying code to the null method. Then the initialization code is there. And so that means if you call this function twice, basically it's a no op on the second call. And then finally, there's a class literal that's created. And so if you ever looked at the end of like a cache.js file, you'll see a bunch of these like create for class calls, and you'll see like what you see basic class names and package names in there. And so what this does is it basically stores enough data for you to do something like class get package or get name. If you do -x disable class metadata, these 3 parameters disappear and the only one is passed as that. And then the class name is synthesized by just class $ type ID.
You're kind of at the end of the time.
Yeah.
So
Let me
Go wherever you want to go.
let me quickly go to one thing that's important. Oh yeah, we wanted to talk about code splitting. Who wants to learn how the code splitting works? Can we go for like 5 minutes on this? Okay.
The next one is Doctor. So
Doctor, do you mind? Is he here?
He's not here, so you can just.
Okay. Okay. So how does code splitting work, right? Basically, we use the control flow analyzer that normally is used to prune dead code. We reuse it to basically do code splitting. What we do is first we traverse the entire program to get an idea of everything that's basically alive and that's going to be preserved for the whole program. Then next, for each split point, we want to try to determine only the stuff that's alive from that split point only, as if the entire rest of the program is unreferenced and would be pruned away, right? But we can't just do it like that. That would be the simple thing you would think, is to start at the run async callback and just traverse out from that. But that actually will give the wrong result, because the exclusive code in there will also refer to shared library code. And so you don't want that in there, because you want the stuff that's only exclusive to that fragment, not the stuff that's also reachable from other split points that's shared. And so the actual computation is you compute the entire program, let's call that P, and then you traverse, for split point 1, I don't traverse split point 1, I traverse all split points but split point 1, okay? And I subtract that from the total program. And what's left over actually is the stuff that's only used in split point 1. So it's a set difference operation. Whole program minus all the other split points equals the stuff that's exclusive to this split point. After we've done that, we have a set for each split point of all of the JavaScript statements that are live in each split point. And then there's a class called fragment extractor that basically, so to be clear, all the bullet points at the top work on the Java AST. Then there's a thing called fragment extractor that starts on the Java AST and slices it up. It basically, using those sets, goes in there and pulls out the pieces that are live for each fragment and shoves those into separate files. And those become like the 1.js.
On the JavaScript AST.
On the JavaScript AST,
yeah.
Yes. So this is the visual representation of it. So you've got the initial fragment, which is the entry on module load. And now I've got a split point A, and there's some exclusive code, and a split point B, and there's some exclusive code. And then I have B and A both call this common AB method, and then you can see that right here. So what happens is, if you traverse the entire program, it's all the nodes, then you traverse this one, right? And if you subtract this from this, you find out that these two are the ones that are exclusive to split point 1. Likewise, when you're trying to compute 2.js, fragment 2, you have the whole program, you've already done it, you traverse this one, and then basically you subtract this one from that, and you're left with these. And that's basically how you end up with the other fragment. Everything else that's left over, though, this part goes into leftovers fragment, which is the highest numbered fragment on disk. So if you have 2 split points, there would also be a 3.js, which is the final leftover code. That's the one actually that gets big, if you're not careful. So finally, after this stuff is computed, the compiler also replaces all calls like with.run async with the actual implementation of it, which is contained in a class called async fragment loader. So if you're ever curious like what happens, look at async fragment loader, and in there you'll see it delegates this class called loading strategy, which you can override yourself. And so the default loading strategy is XHR loading strategy. So it will do like an XHR to fetch like 1.js if it hasn't already been loaded. And if it has been loaded, it will call a method called wit install code and pass the string of the program, which then is evaled into the rest of the program, patched in essentially. But you can change the way that works if you want to.
So this would be the right place, for instance, use the HTML5 file system API to store that on disk.
Yeah, you could change. You could have a file system loading strategy, for example. And so let's see. Okay, so I'm finally at like the last thing that I was going to do. Is Scott code here yet? No. Okay, so I'll just go on, which is linkers, right? What do linkers do? Basically, linkers take input artifacts of one type. They produce artifacts of another type. Most of the linkers deal with abstract artifacts, but some emit a subtype called emitted artifact. And emitted artifacts are subtypes that actually get written to disk. Those are the things. If a linker emits an emitted artifact, that actually will make it into your war directory. And so, what are the point of these linkers? What do you use them for? Well, there's 3 types of linkers. There's pre-linkers, post-linkers, and primary linkers. Probably the most important linker of all is the primary linker. And the job of the primary linker is to generate the nocast.js file. It's really basically to create the structure of your application. So after a git compile, if you ever look at the disk and you see that there's like a directory called module name, and inside there's a nocache, and then there's several .cache files, and there's also all of the stuff that came out of client bundle, and then there's a deferred JS directory with your async split points. That was all set up by the primary linker. But there are other types of linkers people write. For example, you can write a gzip linker that just compresses the JS and leaves .gz files in the output. Think of them as filters. Some people have written app cache manifest linkers for like mobile devices. There's Chrome extension linkers. The SLOIC report and the symbol maps are all put by linkers. I don't recall any pre-linkers, but that people have written. But pre-linkers, like one use of them would be to emit something, which would then be an additional input to the primary linker, so the primary linker would see it. Okay, so the bootstrap process. How does the nocast.js script actually work? This is controlled by the primary linker, and most primary linkers are rooted at selection script linker, which is basically the bootstrap file is called the selection script. Pretty much all linkers, though, a few years ago, were rewritten to set under a more flexible linker called the cross-site iframe linker. And this linker is really configurable. So if you ever want to change your primary linker and do something special, don't look at subclassing cross-site iframe linker because it's like super configurable. And so what does it do? Well, basically it reads in this template file, cross-site iframe linker.js. It's in the GWT SDK, and it's got pieces in it like underbar, 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 some symbol underbar, underbar that are replaced by this linker file. And some of the things it replaces is the property providers in your module file. So if you like the user agent, the thing that determines the user agent, the thing that determines the current locale, the thing that looks for example, in the URL for the log level, those are like little fragments of JavaScript that people use to find in the GWT.xml file, and those are basically dumped into the selection script in certain chunks of the template. But there's also the need to map a set of property values that have been computed to an actual permutation. Like what does Safari English, let's see the diagram here. What does, for example, Safari English map to, or IE6 German map to, like which file on disk? And so there's a tree, which is really like a multi-dimensional array that's emitted by the selection script linker. It basically is like a giant table lookup, and it will have things like, you know, Safari, German, logging level severe is this, you know, md5.cache.js. And so that's another thing the linker does. Here are some other things. So it does also. It sets up support for super dev mode. So there's a magic variable called GWT active modules, which basically is a list of all the module names that are in the page. It processes meta tags, but I don't know anybody who uses this anymore. It computes the module base, like where was the GWT module loaded from. It can be different than the host page that your app was loaded from, so it has to figure that out. It loads external style sheets, and basically it kicks off the loading of the cache.js script via different loading strategies. And the cross-site iframe linker supports many different loading strategies. There's direct install, which is you put down a source script tag, and it just loads it. There's XHR one. There's one called already loaded strategy, which is basically like it will just like embed the entire, like it will assume that the script has already been loaded and all it has to do is just run it. It'll call the start entry point at the end of it. So you can, this is super flexible, so you could define many different ways to load modules. Like you could override this, the way it kicks off the load of the script and load it from local file system. You could fetch it from index database. Or
So actually, I'm going to suggest.
I think I'm done.
Okay. I'm going to suggest that if you can also do a more detailed breakout session.
Yeah. No, I just wanted to cover linkers basically because the selection script is often like some of the voodoo that people don't really look at how it works. That's it, basically.
Okay.
Question?
I'm thinking that maybe we should, if people are really interested, we could read sort of a breakout and the action. Right? So I'm going to say we're already kind of behind schedule. How about a 5-minute break and 10:45 start? Right?
How far are we behind schedule?
We are half an hour behind.